Hello, welcome back to my channel, Wild Mechanical Engineer. And this time we are talking about pump testing. This pump testing I made it around, I think, 8 years ago when I was an engineer in one of big pump manufacturer. So I would like to share how I did pump performance test in the past. I involved myself. I installed the pump by myself and the team, of course, and we test the pump uh, performance because the pump performance are very important to know because when we are selling the pump to the customer, we promise uh, to them how pumps will be performed to meet their requests or to meet their requirements in their installation. Maybe they are oil gas company or petrochemical company or industrial company that using pump. Okay, straight to the presentations. Let's see the next page. uh, in this page, as you can see, pumps performance are tested based on the standard or norm ISO 9906. And in this ISO or norms mention that how the pump should be tested, and also guide or mention how the test bed or test rig should be built to meet the standard or requirements. Okay, and in these presentations I will show you how the test perform and how the data process and then display to show the pump performance. Okay, let's go to the next slide. Okay, why I make this slide pre-test? In case you are planning to test the pumps, but based on my experience, you have to follow some um, requirement or some step to avoid any risk during the pump performance test. Okay, first, the pump and motors, yeah, connected, of course, joined by coupling. Before testing the pump, you have to make sure that motor shaft and pump shaft connected with coupling. Here is a flexible coupling. Usually flexible coupling should be aligned, yeah, to avoid excessive vibration during the testing, because some of the pump performance test requirements, especially for API application, um, it needs some record about the pump vibration during operation or during tested, because high vibration will make the pump more shorter in service or more needs maintenance or even damage the pump itself faster than expected. So sometimes they need vibration test. And then pump and its frame after assembly, it should be rigid to the floor, yeah, because the energy from motor, centrifugal force from the motors, uh, you don't want that pump suddenly moving or the frame suddenly moving to the right or the top. So you have to ensure that pump stick very well to the base frame and frames very well to the floor. And then you have to make sure the cables from the motors connected to your control panel should be correctly chosen, yeah, and correctly tightened. And Next, you have to ensure uh, the correct rotational direction of these pumps, because when you connect the cables, yeah, you may face that the direction is incorrect, and you need to modify it to the correct direction. You have to see the pumps. Usually there is a arrow there, yeah, on the body of the pump to mention the correct direction of the pumps. And then you have to check also lubrications of the pump, because sometimes pumps it has lubrication housing, so you don't want to test the pump and no lubrication and then generate heat, excessive heat to the pumps and damage the bearing and etc. Then all instruments, yeah, in your test rig should be valid on calibration, all or already calibrated uh, to meet the standards. Usually you need to calibrate the instruments such as flow meters, RPM meters, power meters, pressure transducer, and etc. at least once a year, to a company. You calibrate it to the company uh, that actually have ability or license to calibrate. Then you also need adequate venting arranged on the main discharge uh, suction discharge suction pump, because the test rig usually is a circular closed loop, so you don't want that the suctions suck the waters, and then when it's discharged, you use test rig actually the level of the water in the test rig, or in the what you call it usually a tank, water reservoir, is lower than uh, expected, and it will make noise to the system. So you have to ensure that at the flow capacity, let's say 100 meter cubic per hours, yeah, there is no shortage of waters during circulation. Okay, then you also have to make sure that suction pipe line is occupied by water, and open the venting to release the air of the suction pipe. When you connect the pipe to the reservoir, usually there is still air there, so you have to venting it to ensure all the air already out of the pipe. Alright, so that's my based on experience pre-test you have to do before testing your pumps. So now we continue our session with how we test the pump and how to process the data and display it as a pump performance. Okay, before that we have to understand first the energy transfer chain of pump system that you want to test it. First, as you can see here, um, here the pumps. Okay, and then you have a coupling here, flexible coupling, and then you have a synchronous motor 3-phase here. This is the base frame, and then you stick the base frame to the floor. Okay, this is the suction and this is the discharge. Okay, the energy transfer, as you can see at here. Okay, the power input to the motor is the electric energy that transferred to the motors, and motors will create a mechanical energy is like rotation, and then the motor, of course, it has efficiency, and the output of the motor power will be transferred to the coupling here, and then the coupling transfer the energy to the pump shaft. That will be called as a pump power input to the pump power input. Okay, and then after rotate the pump, yeah, and then pump will transfer the energy into the waters that uh, flowing from the suction and finally discharge. And this transfer of energy and will increase the pump pressure at the discharge site. And this usually the energy transfer done by impeller, pump impeller. Sometimes the pump impeller is a centrifugal type, or sometimes axial type, and also sometimes mixed between axial and centrifugal. So this is the energy transfer chains of the pump. So we have to understand first how the energy transfer and change to mechanical energy, and from mechanical energy transfer into the to the water, and then we call it as hydraulic power of the water after energy transfer to it. Okay, this is typically a test rig of the pumps. As you can see here, we have a big pipe in, and small one. This depend on the how big your pump suction that you want to test. And this is a reservoir of waters. Actually, there is a very deep uh, water inside, yeah, at least 4 meters, and the volume of it, of course, depend on your design test rig at what meter cubic per hours that you can test into your test rig. You can you define it based on your need actually. From this test rig, as you can see, there is a suction valve here, usually butterfly valve. And then let's say for example you want to test the pump here, and the coupling here, and the motor here, and connect it here, and water in, and the discharge you put it back into here, yeah, and then circulate it in closed loop. As you can see as well, you have some instrument as shown in the photographs. You have here what we call it ultrasonic flow meters. Okay, before these equipments used in industrial, a long time ago, the flow measured by difference of pressure at the 2 point, so we call it as Venturi meters, yeah. But nowadays they use ultrasonic flow meter at discharge to measure the flow. Okay, this is the clear view how the ultrasonic flow meter installed here, and this is the display of the flow capacity of, of water flowing in the pipe during the testing. So as you can see, cable here, this will be connected to this panel, and during the testing you know how much the flow capacity of the pumps. And then you also have pressure transducer. This is a ABB brand, yeah. It measures the suction and discharge of pressure of water during the testing. And then you also have a power meter here. It's, this power meter to measure how much power actually absorbed by AC motor during the testing at specific flow capacity. And for data acquisitions, you may need here a PLC system and data acquisition systems. Let's say you want to have a test rig with uh, controllable system. For example, you control the opening of the valve and to reach specific flow capacity from computer. Yeah, so you don't need to climb or to control manually, and it depend on your needs actually. But mostly in pump manufacturer, they make it more automatically to ensure that testing done in the more efficient and effective way. So they invest some amount of money to have it in the test rig. Okay, another equipment they may you need, yeah, is a temperature sensor. This infrared temperature sensors, and also you need also RPM meters, infrared with deflector and etc. to measure how much is the pump's shaft rotation during the testing. Okay, next we have a testing procedure that we have to follow. It's very simple procedure. Let's see from this flow chart. After the pre-test you have done, and then we go to the testing procedure. Let's say for example you are ready to test. You install the pump, piping, everything, etc. The leaking already no more in the piping in this piping system. Water is enough, and etc. And then you open the valve, let's say for example 30%, and running the pumps, and to make it warm, let's say you wait until 5 minutes 10 minutes to ensure it warm. Then you need to check the pump rotations correct or not, but you don't need to wait 10 minutes actually to check the pump rotation. You just see uh, how the shaft rotate compared to the correct pump rotation. If wrong, you have to modify. Let's say your pump rotation already correct, then you need to continue, yeah, until it mechanically stable. Let's say 60 minutes, but I think 60 minutes too much. Based on my experience, only 15 minutes, yeah, to wait everything okay and etc. to check if the pump bearing is not so hot, vibration is not so high, and etc. And then we continue. Okay, then uh, before testing, of course, you have a data sheet of the pump. So this next step, you better prepare it before testing the pump. Yeah, you have to divide how many point of testing you want to perform. Yeah, and then based on the standard of ISO, you have to test at least 5 point. The first point is a shut-off point where the valve of discharge you fully close. The suction is of course must fully opening, and we call it shut-off situation, and run the pumps. Yeah, and of course at the shut-off there is no flow recorded from ultrasonic flow meter, because typically arrangement is like this. For example, you have pump here, this is a suction, this is let's say discharge, you have a valve at discharge, and then you transfer back into the reservoir. Usually at least, yeah, minimum 3 times of diameters valve located here. The more it's far, the more it's better. And then usually you have ultrasonic flow meter here, and minimum distance 3 to 4 5 of diameter of valve, to ensure that the flow of water in the pipe is not really turbulence. Yeah, there is the so the correct measurement by ultrasonic flow meter will be better. With so much turbulence, it's not so good for the real measurement. Okay, after you divide at least 5, let's say let's say you want to test the pump performance with design flow capacity 100 meter cubic per hours. So you have to test at 0, okay, and then at the design point 100 meter cubic per hours, and then 120% of its design points, and then in between minimum and design points, okay. So you will have at least 5, yeah. Okay, um, then from that point of flow capacity segregation, let's say you want to test first at shut off, yeah, shut off here, 0 flow capacity, and you record the pressure at discharge, okay, and then you also record the pressure at suction, okay, and then also you record the flow capacity, of course 0, and then you record the how much the speed, rotational speed of the pump shaft, and then you record as well the power in to the motor during this condition. This is the example of uh, calculation of how the segregation of flow capacity being done actually, okay. Then as I mentioned before, you record the velocity head suction by by transfer the flow capacity at sort of point, for example, of course 0, but at next test, this point and this point, this point and this point and this point, you have to record the pressure at discharge, and then the RPM, okay, and also you have to record uh, power, yeah, power into the motor, yeah, okay, and you move to next section, to next flow capacity, to the next flow capacity, to the next flow capacity, and then to the next flow capacity. Okay, in this figure you see I have a pump here. This is a motor. I have here's pressure transducer connected to this pipe at suction, yeah, and then I also have a pressure transducer around here, yeah, connected to this pipe, yeah. Let's say you go for the next flow capacity. Let's say in this example the flow capacity at 73.5 meter cubic per hours. Of course, by formula you can get the, actually we call it a head velocity at suction and also head velocity as discharge, and at this point you also collect the speed of the shaft, yeah, and also you collect the pressure at the suction, and you collect the pressure at the discharge, and here there is a power meter. You also collect the power in to the motor at that specific flow capacity. Okay, this is another clear view how the pump runs and during the testing. This is the suction. This is the pipe tap to the, we also tap it to pressure transducer, but pressure transducer here is not more is already digital pressure transducer. In the past they use manometers to measure the static pressure at suction and at discharge. Now they put it more electronically, and then you calculate, of course, the velocity head at discharge using this formula. This is international unit combined with imperial unit, yeah. So no problem. It's only how to perform in other unit. Okay, and then you also need to understand that before testing, uh, let's say you have a pump here. Okay, this is the suction and then this is the discharge. So if you tap here the pressure transducer to read the suction pressure, and here is pressure transducer to read the discharge pressure. You have to understand that the distance, the difference of this stand, yeah, how much is the difference? Because we want to know that the testing points of this uh, rig, so that will be weakness of delta z. Yeah, okay. And during the testing, of course, as I mentioned, you need to have information of the suction pressure, and you have to translate this suction pressure into, we call it suction head, with this formula. Others formula also no problem, as long as you maintain the unit. And then you need also to have a data of discharge pressure, and then you will translate this to discharge head. And then after that, you have the data. Yeah, you will need to calculate what you call pump total head. Is pump total head equal to head of the discharge minus head of suction, and plus we call it delta head of the delta velocity pressure, velocity pressure, and delta z. Yeah, this delta z is the difference of the measurement point at suction and discharge. This is some example of the calculation. Okay, and then you also need to calculate how much actually power into the motor during the testing at specific flow capacity. You know that motor, it has a graphical performance. Yeah, the power generated, yeah, the power generated, for example here, let's 50 horsepower. Yeah, at this current, record the current here, and then you have a power factor here. Yeah, and from this you need to understand that power input to the motors, yeah, uh, you record, but the power output of the motor you measure with the uh, power meter and etc. But sometimes you need to see the motor itself performance at the specific currents, yeah, how much power generated and how much is the power factor of this system. So this is the calculations, manual calculation of the powers input to the motors. You have a voltage here, you have ampere, and you have power factor, and you have a square tree, and then this is will be power input to the motor. But the power factor of the motors actually is depend on the current, or the load of the motors. So as you can see in this graph, um, the power factor is not linear compared to the current. Motor, AC motor itself, it has actually a graphical performance itself. So why we need this? we need to understand that it's not linear correlation between ampere power and the power factor, because if not linear, yeah, you have to ensure that the correct power, actually how much power sucked by the pumps or transfer to the motor and transfer to the pump itself. But in modern test rig or industrial or manufacturer test rig, they use actually a power meter. This usually Yokogawa brand or other brand, just to make sure how much actually power in to the motors. Okay, and then we want to know the power output of the motors. This is quite tricky. Uh, the power output of the motor is usually they call it a shaft power of the motor. Okay, then you need the motor performance that data sheet actually. So let's say you 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 running the motor at this powers. You have a power factor, yeah, and then you have efficiency here. Okay, so it means the power out of the motor, yeah, is of the motor is not equal to the power in. So there is a losses there. So that is why you need this graph to know that how much actually motor transfer the energy to the coupling, and from the coupling to the pump shaft. Okay, this is another characteristic of AC motor that you need to know. But in the past, to know the output power of the motor, they have a simple test rig actually. Let's say you have a motor here. Okay, they they have a arm here, yeah, and the motor is arranged with free movement to rotate, yeah, but better with the this view. That's this motors, and there is arm here, and the motor is connected to the system that not fixed. So when the motor rotate here, there is a counterbalance to here. So uh, you you need to feel here, let's say uh, another counterbalance from steel to ensure the motor is straight, not tilted or etc. And when it balance already, you measure the how much weight you put to make it balance, and the distance from the center line you measure it fixed all the time, and you will have the power, yeah, will be torque multiplied by RPM, yeah, and this torque will be equal with the mass of this counterbalance, yeah, multiplied by the arm length, yeah, and then this is will be considered as how much power actually transferred by the motor into the pump. Okay, after you collect all the data there, uh, you have flow capacity data here, at least 1, 2, 3, 4, 5, 6 point, and then you have a head of velocity at different flow capacity pressure, and the head of the distance, yeah, delta z, yeah, and then you have a head total. The head total formula, as I mentioned before, uh, calculated based on here, based on this formula. Okay, then you record the amperes, yeah, and after that you have a power motor in, you have the efficiency of motor, and then you have the power motor out that transfer to the coupling, and from the coupling into the pump shaft. So you have this data already, and you tabulate it. After you have this data, you need to perform what we call it affinity law. If you go to the university, there is a course, yeah, um, fluid mechanic course. They also talking about how fluid mechanic perform in the field of pumping system. So they have affinity law, because pumping is not very easy to measure or to define with. So this affinity law actually generated based on the test on the lab. Why? Because we need proven correlation, that not theoretically anymore, because the level of complexity of water flowing is very hard, yeah. So they generate affinity law. This affinity law, as you can see here, yeah, when pump running at different speed or rotational speed, it will create different flow. The correlation between speed and flow is linear, as you can see here. So why we need this? Because we need to generate the pump performance, yeah, performance at fixed velocity or rotational pump or sub rotation. So this here, different situation of the pump rotational speed. So we need this affinity law. Okay, then you also need affinity law correlation the speed to the total head. Is the correlation based on the laboratory test that already proven its correlation, that correlation is square compared to the head. So it means if you modify the pump speed, the head will be modified, no more linear like before compared to flow. It will be exponential. Okay, and then there is also affinity law for relation to the power. Yeah, it's no more exponential. It's you need more higher exponential. This is exponential 3. Head is exponential is 2, and this is a 3. Okay, there is example calculation here actually to make it a bit clear. Then after that you collect, yeah, you need as well to generate the pump efficiency at constant speed. The constant speed here is related to here. You have a table here, yeah, and then you need to generate another table at constant speed, yeah, another table at constant speed, and then you will get new number of power in, head of total head, and etc. Following the affinity law. And then here you have a pump efficiency at constant speed. Let's say the speed here is 300 rpm, and then you generate the pump efficiency at a constant speed. So but before go there, you have, as I mentioned before, you have to change the first tabulation to the new tabulation at constant speed. So you modify everything, yeah, at the constant speed here. Your, let's say this constant speed is the motor chosen, or the speed that you offering to the customer. This is the design speed of the motor, and that unfortunately the speed of motor will not always the same motor to motors. It depend of efficiency extra, but you need to make a pump performance test at the constant speed. But you cannot get you never get to constant speed, but you transfer theoretically to constant speed. So you have a new table here. The correlation of the speed, yeah, of course you have to follow the affinity law. Head is exponential 2, power is exponential 3, and correlation to the flow capacity is linear. After you get there, yeah, after you get there, so you will have pump efficiency here. You also have power output of the pump, yeah, and you have a power input of the pump. I mean the power into the pump and the power output of the pump. So if you compare the power output of the pump divided by power input of the pump, so you have a pump efficiency. But how to calculate the power input to the pump? Yeah, as you know that before we have we call power motor in and power motor out. Power motor out, yeah, you have this calculation. Is a power motor in, you measure by this power meter and multiply by its the motor efficiency, and you have a power motor out. And if you don't consider the efficiency of the we call it the losses inside the coupling, and you can directly say that the power output of the motor will be the power input to the pump. Okay, and pump efficiency is calculated like this. The power output of pump, we call it hydraulic power, yeah, it calculate based on this. It's a specific water density, gravity, flow capacity, and the head totals. This is the example, yeah, for the flow capacity. This you have this head total at this RPM, then you have a power output of the pump, yeah, this one. And what is the power input to the pump? The power input to the pump, as I explained before, it will be the power output of the motor. Okay, and then if we compare the power output of the pump divide the power input of the pump, that the power input actually that considered as a power output of the motors, then you have a efficiency. So you have the value at least 2, 3, 4, 5 point, and from this point you generate pump efficiency. As you can see, the pump efficiency is it's not linear, yeah. At some point it will be dropped. Why it drops is another topic, yeah, considering the eddy current, etc., and the limitation of the pump itself. Okay, and before we continue, you know that this pump tested using waters, yeah, but in real life maybe the pump is not applied to the water, maybe for the oil. So in this case there is a scale lab scale testing that if pump then used for another fluid, let's say natural oil, or let's say petrol and etc., with lower specific gravity than water, then there is a simple formula that at lower specific gravity compared to waters, you will need less power. It makes sense, yeah. So this is the formula for that, and this is the power required, yeah, the power required to the pump, yeah, to generate head and at specific flow capacity. But if you use this pump to transfer petrol with lighter than water, then the power you need is lower, like this. Okay. How about the effect of viscous fluid? Viscous fluid is, let's say, a fluid that with higher viscosity. Yeah, higher viscosity mean the fluid is more, you know, more stick to each other. It's it's more viscous. So how its effect? Yeah, the effect of this also tested based on scale lab. There is many book viscous effect into the pump, yeah, and they come with uh, formula that uh, at the specific speed, yeah, at the specific speed, the viscous of fluid actually will generate different situation to the head, yeah. Okay, let's say for example here we assume that we pump fluid with the properties like this, yeah. Okay, and then this is, you have efficiency, head, and etc. Okay, but when you change the viscous, yeah, then you need to change the effect into the flow, head total, yeah, and this will be the new numbers for the flow, yeah. Let's say the fluid more viscous, more stick to each other. When you have this performance on the lab that tested with the water, that with other more viscous fluid you will have this number, yeah. So you have to follow this formula, but this formula is a bit complicated, but there is actually chart there, yeah. This charts, you move from this direction to this direction to this direction and to this direction and to this direction, but we can forget it for a while, because this chart actually uh, more needed after you test the pump, and then you ask the suppliers what fluid that will be transferred by this pump, and you combine if this um, pump still able to meet the customer requirement. Okay, and another effect is the viscosity effect to the power input to the pump. Of course, more viscous the fluid, you need more powers, yeah. So the formula is like this. We tested the pumps with cold waters at the room temperatures, let's say 27 Celsius degree. But when you use to transfer the when you use the pump to transfer the natural oil, yeah, that more viscous, you need more power. And how is the effect of viscous fluid into the pump efficiency, of course it will create pumps efficiency worse than before. So it means if you use the pump to pump more viscous fluid, the efficiency will drop. So you have to consider this when sizing your pumps. Will it be used for viscous fluid or water? So if you use to the viscous fluid, so you mean you need to modify the pumps you need, because the pump performance showing in any dataset, yeah, is when the pump tested using cold water or water at the room temperature and the room pressure, is not showing when the pump used for fluid that you need. So you need a conversion table. Yeah. Okay. So that's for all. Yeah. So to summarize this presentation, I would like to repeat again. Okay. Before you want to understand how the pump tested, you have to understand the energy transfer in the system. Okay. Electric energy transferred to the AC motors. AC motor modify electric energy become mechanical energy, the shaft rotation. The shaft will be coupled to the pump shaft and the transfer to the pump shaft, and the pump shaft rotate, yeah, and transfer the energy into the impellers, and the impellers of the pump transfer the energy to the waters. Okay. So based on the norm, yeah, or the standard ISO that I already mentioned before, during pump performance test, you have to divide how much flow capacity you need, yeah, to test at least 5 point. Start of point, base efficiency point, 120% of the from base efficiency point, and then and etc. And let's say you start from start of point, you measure the pump suction pressure, pump discharge pressure, rotation of the shaft of the pumps, and the power input to the motors from let's say power meters, and then the power output for the motor. You check your motor data sheet at that point, specific point, how much the power factor, and then you know actually how much power out from the motors. And by ignoring the efficiency of or the losses of energy at the coupling, you just mention that the power output of the motor will be directly with power input to the pump. So of course when you change the capacity, the motor's speed will be different, yeah, and you change again to have another some data, the motor of speed can be different, but you need to represent the pump performance at same motor rotational speed. So that is why you need, we call it affinity law, as we discussed before. So this affinity law, after you gather data, you have to transfer all those data rotational speed to this single speed, and then from the single speed you transfer how much the correlation to the head, how much the correlation to the flow capacity, how much correlation to the power input to the motor, and from that point, yeah, you generate the pump performance chart. Okay. Yep. So next video we'll talk about net uh, pressure suction head required. This is quite interesting, because if you never test the net pressure suction head of the pump, yeah, by yourself, actually it's very hard for you to understand what is the meaning of this testing actually. That will be our next video. Thank you.